to the fourth exercise session. Today we'll be having a look at functions, and in that I mean we're going to have a look at mainly function transformation, logarithmic and exponential functions, linear and quadratic functions. Of course, there are other types of functions, namely a very important set of geometric functions, but those will be for next week. If you have some doubts about this, I strongly encourage you, as always, to go over the theory overview. Not only will you find an overview of the rules of working with logarithms and exponentials, rules of factorials, you'll also find some rules on how to work with transformations. These transformations will be the second part, but first and foremost, we'll start with logarithmic functions. So basically, what is there to know about logarithmic and exponential functions? Much like adding and subtracting are inverses of each other, multiplying and dividing are inverse operations of each other, so is taking the logarithm and the exponent of something. These are inverse operations. So this is also what the first question is about. So you have to basically deepen your understanding about logarithmic and exponential functions. And the idea is that you, first draw some kind of exponential function. You can draw whatever you want. You can draw, let's say, 2 to the power of x. This is a typical form of exponential functions. And then, after drawing this, you figure out for yourself why a logarithmic function that looks much like this, so it would be this guy, is actually the inverse of this. And for this, of course, you know that when you are interested in inverses, what you basically do is you have to mirror the function over the y is equal x function. This you can do by using a mirror. If you don't have a mirror nearby, your smartphone screen when it's completely black is a good alternative. Okay, so assuming that you understand why these are inverses of each other, let's see what we can do with them. And for this, we're going to go immediately to exercise 2. So exercise 1 is recommended for home. And then we go to exercise number 2. And the first exercise I want to make with you is 2a, where it says that where we're interested in calculating the logarithm with base 2 of 16. So logarithm with base 2, logarithm of base 2, basically it means that it's the inverse of the exponent with also base 2. So this exponent we just talked about. So we're interested in what that's equal to. And let's call that a. So now how can we calculate this? Well, the thing is, knowing that the inverse of this is, 2, an exponent with 2 as base, maybe we can try and cancel this out. And this is actually interesting because just like we can multiply both sides times 5 or divide both times 5, and we are actually not changing the equality, it's much the same with exponential functions and logarithmic functions. So what can we do? We can say, 2 to the power of a, and then on this side, 2 log 16. So we did the same operation on both sides. We basically made them exponents with base 2. And the neat thing about this is that on your left-hand side, because exponent of 2 and the logarithm of 2 are the same, are inverses of each other, they cancel each other out. So what do you find? You find that 16 is equal to 2a. So now the question is, how many times do we have to factor 2 to reach 16? And the answer would be 2 to the power of 4 is 16, right? So you could say a is 4. Of course, you cannot always neatly calculate these things, and sometimes, you will need your calculator. Maybe a nifty trick. In your calculator, you will only find 2 types of logarithms. You'll find the normal log, or you find ln. So what do you need to know about this? This is basically the logarithm with base 10. Or this one over here is actually the logarithm with base e. Remember from previous video, e was 2.7 and so on. Okay, and there's a way of converting any logarithm over here to have these bases so you can actually fill it in on your calculator. So how would you do that? Log 216, and for this, I'm just quickly going to write it down, but you have, of course, the theory and the theory overview to have a look at why these formulas are what they are. But then you would basically you just get log, which means log base 10 of 16 over log 2. So you can always verify it like this. Okay, then 2b, I'm going to recommend you make that one at home. And then I'm going to make one more of this set, and it's going to be 2e, which says ln of the square root of e. And we have to calculate this. And again, you can do pretty much the same as what we did before, and in that case you would write, okay, we want the inverse of ln, which remember it's log e base e, so you're going to say, well, exponent ln square root e is equal to e to the power of a. That's one way of finding your answer. Or another one is if we immediately start rewriting this a bit, and you say ln e to the power of 1 over 2 is equal to a. These two things are also the same. Okay, and what can we say then? Well, because of logarithms, you can move this exponent to the front. And here, be very careful, the exponent is within the logarithm. If it's over here, you cannot do that. So you get 1 over 2 ln e is equal to a. Okay, now ln e, because they're inverses of each other, they just cancel each other out, and you find that a is 1 over 2. This would be much the same for this exercise. If this doesn't make sense to you, please reread the theory, have a look at the lectures again, because while logarithms and exponential functions are a very important part of being an economist and modeling all kinds of behavior of stocks of people, you really need these things. And also later when you go into statistics, much of the distributions you will be studying are actually constructed with exponential or logarithmic functions. So really have a look at it and try to really make sure that you understand these things. Okay. That being said, let's move on to question number 3. Oh, maybe before I move on, there's a couple of important things, and well, of course I hope you can discover it, but the logarithm of 1 is equal to 0. Try to verify that for yourself. And then the other thing is, well, is it possible to take the logarithm of a negative number? Is that possible? Well, especially within the real numbers, try to work that out once and do it with this logic. Is it possible to reach this thing? Okay, that being said, let's move on to question number 3. Question number 3, I'm gonna leave, well, let's first do question A. Because basically what you have to do here is just mess around a little bit with these exponentials and logarithms and try to use, well, the rules to your advantage to try and simplify these things. So you get here 3 to the power of x plus 1 plus, excuse me, it's not immediately 3 to the x plus 1, it's 3x plus 3x plus 1 is equal to 4. Okay, so this looks like kind of a difficult question to answer, right? Or you might see it by heart, but I could change this thing over here and make it more difficult. But there's a way to simplify these things. And basically what you could do is say, well, these 3 to the power of x and these 3 to the power of x plus 1, they look very, very similar. Let's see if we can maybe factorize them or simplify it. And for this, well, we could rewrite 3x just the same, and then 3x plus 1 is nothing more than 3x times 3 is equal to 4. Okay, and now you should see how we can factorize this. By bringing out 3x, you find the following. Let me respect the order of what was written there. Of course, it doesn't really matter. Is equal to 4. So you find 3x times 4 is equal to 4, or in other words, 3x is equal to 1. Of course, what does x need to be equal to? x needs to be equal to 0, because 3 to the power of 0 is indeed equal to 1. So that's one way of solving it. Okay, so that for simplifying with these exponents. And basically, if we ask you a question like this, you will always just need to use a couple of one of the rules that's written all the way at the beginning in the theory overview. Then let's have a look at f. F, you say log x plus 1 is equal to log 24 minus log x minus 1. Okay, and this is the interesting thing about logarithms, is that, well, when we add them or subtract them from one another, and if they're on the same base, which is of course is the case, let me write the bases here too, so it's just a simple log, that means that they're all on base 10. This is just the agreement everybody made around the world. Okay, so first things what we can do is just, well, let's leave this logarithm of 24, which is just going to be a number on one side, and let's move x to the other side as we're used to. So we can say, well, log 24 is equal to log x plus 1 plus log x minus 1. You can then use that, because these are on the same identity, there's actually a way to contract them. And why does this make sense? Of course, refer to your theory, but basically it has to do with actually these being inverses of exponents, right? And so that this is kind of like, in a sense, like a multiplication. So what you get is actually x plus 1 times x minus 1. These things are equal to each other, is equal to log 24. Let's simplify it then a little bit, and what do we find? Well, we find that log x squared minus 1 is equal to log 24, by just working this out during the distributive, or you could actually see that these are complements of one another. Remember the a plus b times a minus b. Okay, now you can say, well, okay, obviously these things between the brackets need to be the same, but if you don't see that, well, you could say, well, okay, these logarithms, they're kind of messing me up. I want to get rid of them. So basically, because these are base 10, you can say, well, let's raise both sides to, well, use x with exponents base 10, so they becomes 10 to the power of what was written. X squared minus 1 is equal to 10 log 24. Okay, because these things are inverses of each other, they cancel each other out. So what are you left with? You're left with x squared minus 1 is equal to 24. You could, of course, already have noticed that this is what you were going to get here. This is more like an in-between step if you would like. So you find that x squared is equal to 25. Or, in other words, x is equal to plus minus the square root of 25, or x is equal to 5 or negative 5. And here we have to be a bit careful, because logarithms, as I hope you understood from the previous thing, they do not allow for negative numbers. Negative numbers doesn't work for logarithms, especially not within the real numbers. So we have to be careful that we're not evaluating the conditions for existence for logarithms, because a logarithm, well, with this thing, x plus 1, needs to be greater or equal than 0. Well, actually it needs to be greater than 0, because it cannot reach 0 as well, and here this thing too, x minus 1 needs to be greater than 0. Okay, so let's see if our solutions are, well, possible. So 5 minus 1 gives us 4, 5 plus 1 gives us 6, not a problem. But minus 5, well, that gives us a problem on both sides. So minus 5 is not a valid solution. So the only valid solution for this equation is x is equal to 5. Okay, so that for A and F, and I'm going to make one more, and I'm recommending that you make G at home. Recommended for home. And then I'll solve h together with u. So in this case, what's written here, it says 2 times log base 100 x squared minus log x, it's just log 10, is equal to 4. And here notice that, well, we cannot do what we did before, because here, well, we contracted these things, right? But they were on the same base, they were both on base 10, while these are not. Of course, there's ways to convert it. You could say, well, we can convert this to base 100, and yes, you definitely can. So remember, with the formula I wrote all the way at the beginning, you could convert it with this, but there is another way of solving it too. And I'm gonna show you that way, but either way is fine. So in this case, well, just as I did before, and I think I did it in slide 1, here this 1/2, I told you could bring it out because of the logarithm, right? But you can also bring it back in if you would like so. So what can you say? Well, okay, great. This is actually, let's rewrite it a bit, and you get log base 100 x to the power of 2 to the power of 2 minus log 10x is equal to 4. Okay, great. And then log x squared is just log x to the power of 4. So let me rewrite it. So we have just x to the power of 4. Okay, so far so good. And now what's actually neat about this thing is that 100 and 10, well, they're factors of each other. So maybe by just raising everything to the power of 100, well, so using base 100, this thing will cancel each other. It will also be cancelled out. And yes, it will, but we have to think about it a little bit. So what we say is 100, and then we're writing everything we had over here. So we're going to use that as our new base. So log 100 x to the power of 4 minus log 10x is equal to 100 to the power of 4. Okay, so far so good. Okay, what else can we do? Yeah, this negative sign, I don't really like it that much. You can, of course, leave it over there, and then basically, well, how could you rewrite it? Well, you could split it up, and then this becomes kind of like a division, but I think multiplications are neater. So basically what's written here is, well, times -1, right? So imagine we just bring that up as we did before, and then we get plus logarithm, so plus the logarithm of base 10 x to the power of -1, right? Okay, so when we have worked with exponents, well, when do we get plus? Well, remember when you do x squared times x to the power of 3, well, that's equal to x to the power of 2 plus 3, or x to the power of 5, right? So we can say the same thing here for this 100. It doesn't need to be x, right? It can also be 5 to the power of 2 times 5 to the power of 3 is just 5 to the power of 5. So we can do the same thing over here. We can say, well, this is 100 log base 100 x to the power of 4 times 100 log base 100 x to the power of -1 is equal to 100 to the power of 4. Okay, and this already helps us a little bit, because now we can easily cancel these two things out because they're neatly inverses. But we're still stuck with this thing over here, 100 log 100, sorry, this is not log 100, this is log 10. So 100 log 10 x to the power of -1 is equal to 100 to the power of 4. But the nice thing here is, well, 100, we can rewrite that. So we can say x to the power of 4 times 10 squared time to the power of log 10 x to the power of -1 is equal to 100 to the power of 4. Okay, and what does that tells us? Well, this 2 is actually just, it becomes 2 times this, respecting our rules of exponents. Okay, and then when this 2 is over here, well, we can actually work a little bit further with that, and we can rewrite it as x to the power of 4 and bring that 2 back into the logarithm, and you get 10 to the power of log base 10 x to the power of -1 to the power of 2. Or in other words, x to the power of -2. Okay, and that's all equal to x 100 to the power of 4. Okay, and this is nice because now we have the same, well, we're working on the same base, so again, they cancel each other out. So in that case, well, what do we still have? We have x to the power of 4 times x to the power of -2 is equal to 100 to the power of 4. Or in other words, x squared is equal to 100 to the power of 4. Or even better, x is equal to 100 squared, or 10,000. So basically what you need to know about these things is how you can use the laws of logarithms and exponents in your advantage. Of course, at the beginning you could have said, well, let's put everything on one base and let's say log 100 of x over log 110, and then work it out like that. That would have also been possible, and you should have gotten exactly the same answer. Okay, so that for the basically the warm-ups of exponential functions. Now let's continue a little bit, and I hope this isn't, well, completely unclear to you. We can try and plot some functions. So, and here I've said, well, the function needs to look, let's write it as I did on the paper. I said fx needs to be equal to log with some base, the one that we have to figure out, and then of course with our variable x. So that's the one we have to find in number 4. And every time what's given is actually a point. And if we look at, for example, question A, we are giving the following point, so 32, 5. So that means when x is 32, y is equal to 5. And now we have to find the function that runs through this thing here, right? So what does this mean? Well, it means that we can fill in these things, because this is just the same as writing y is equal to log a of x. Both of them are just saying this is a function, right? This just tells you a little bit more. It tells you that your function has a variable x. We can fill this in and we can say, well, this means that 5 is equal to the logarithm with an undetermined base a, and then x is 32. So, because that's the only way that we could find a logarithm that runs through these things. So now we have to find this a over here. So what do you say is, well, okay, this logarithm, I find that hard to calculate, especially because I don't know base a, but there is a way to do it. So you can say, well, I want to get rid of that logarithm over here. Exponents are much nicer. It's much easier to calculate with them. So you can say a to the power of 5 on both sides. And here's you say a log a, so you're introducing an exponential with base a on both sides. On the right hand side, this neatly cancels out. And you find that a to the power of 5 needs to be equal to 32. Of course, if you see this immediately, what your answer is, you don't have to go through all the steps. It's really just showing how to do it. So here we have to find some kind of base, and if we raise it to the power of 5, we need to get 32. And of course, we picked something that's doable, and it would be a is 2. So we can rewrite it as our function, and we can say our function fx is equal to log base 2 of x. Of course, there's much more you can do to logarithmic functions. You can make the function much more difficult, and you can do some kind of disturbance on it, but in this case we really wanted you to just work with like really the elementary logarithmic functions where you just try to identify the base. If this makes sense to you, then you can move along with me to exercise number 5. Otherwise, a good exercise to make would be exercise B. Okay, so now we go to exercise 5, and again it's just mainly applying all these rules of logarithms, and there is not really a trick on doing this. You just have to solve many questions on them, and at a certain point you'll start understanding how these rules work and when some rule is better to apply than another. So practice is the only solution in this case. And I'll solve question A with you. Question A, so we get a logarithm base 3, 5, and then it continues. We get logarithm base 3, 18, minus 2 logarithm 3 square root of 10. Okay. And I tell you can simplify this. So there are a couple of things you could notice, and the first thing you might notice is that they're all on the same base. So that's nice. But then we're still we have these 2 over here that maybe we'd like to work away before we start contracting things and putting them all together. Well, this 2 is actually very neat because, well, we have this square root over here, because we can rewrite it as log 3 of 5 plus log 3 of 18 minus the logarithm 3 square root of 10, and then we bring in the factor in front of it back inside, so we get to the power of 2, meaning that they neatly cancel each other out. The square root and the power of 2. Okay, now, because they're all on the same base, well, we can bring them together, and you can say log 3, 5 times 18 minus log 3 of 10. So in this case, you find, okay, log 3 of 90 minus log 3 of 10. And then here, well, basically you can contract it again, but here, careful, because it's not a multiplication. It's not going to be a multiplication anymore because there was not a plus in between. How can you solve that? You can say, well, I can make it plus by doing the following. Of course, that would work. Or you can just say, well, minus, and actually you're just doing the same thing, it's the same logic. This minus sign means that you have to divide them when you bring them together. So it means that you get log 3 90 over 10. So that's your new solution, your new exercise. Or log 3 of 9. So what's that equal to? I'll let you think about that for a bit. So you can work it out the same as we did before, but basically what you want to find is to what power do you have to raise 3 to get 9. So you find that actually this entire thing is equal to 2. And this is, you can simplify them and basically get out of this way of really writing complicated things. And the main thing what I really want to that I want you to take away from it is not only to work with these, well, these functions and these operations, how you can, well, basically cancel stuff out and stuff, but the main thing I want you to remember is that this thing is of course just a number. So log 5 is just a number. ln 5 is just a number, right? ln pi, just a number. It's all just going to be numbers. So as long as there's no x in it, it's not a function, it's just a number, right? Because you just perform some kind of operation on this number. Okay, so that's basically it for exponential functions. For 5, it would be good if you make 5c. I'm going to recommend you do that one at home too. This one is interesting because, well, you cannot really calculate your base, but you can simplify the function a lot so that it looks a lot neater. You can contract it all into one term. And then we're going to move to the last exercise of the video, and basically we're talking about making inverses. And the thing about inverses is that these are nice, and in some cases very useful when you get to economics. Like basically if you find some kind of data, you find some kind of pattern and it doesn't make sense, or basically it's not linear, and well, we like to work with linear things in statistics. You'll see more about that later. Sometimes you can convert it by being clever with your inverse functions. So to find an inverse function, it is not always possible. Well, you can always find partial inverses, but it's not always to find a full inverse. So imagine a function like this, which is just going to be x squared. Well, there is a way to find an inverse of this. Basically, you mirror it over it. But the problem is that if you find the inverse, this guy over here, this is no longer a function. Because, well, meaning that you cannot draw one vertical line through it and only hit the function once, you're going to hit it twice. Or in other words, if you have your initial function and you drive a horizontal line through it, and you're going to basically touch the function twice, it means that, well, when you take the inverse, either it's not going to be possible, or you're going to find partial solutions or partial functions that together will make you the full inverse. Okay, that being said, the process of trying to find inverse is pretty simple once you know about it. So A, we get the function 5x minus 1. And now what's the trick in finding this function over here? And well, it's just going to be a line, so basically this is not really going to give us a problem. It's going to look like this. A bit more down, it's going to look basically like this, the function. We can draw one horizontal line through it. So finding an inverse is not really going to give us a problem. So what you do is you say, well, fx becomes your new variable, and you're going to call it x, right? And then you say, well, before everything that was x is now going to be the inverse function. So f to the power of negative 1, x minus 1. And now, of course, you wanna find a function here, right? So what you need to do is, well, rewrite it a little bit so that you have this f to the power of negative 1 of x on one side. So in this case, well, you say, okay, you get x plus 1, moving that to this side, minus 1 x, like this. So you say, well, let's divide both sides by 5, and you find x plus 1 over 5. And these are going to be the inverses of each other. So meaning that if you do an operation, well, if you use this function as some kind of machine that gives you takes an input and gives you an output, for example, the input is x is 1, it will give you an output of 4. If you do the opposite here, you would find again x is 1. Verify that for yourself, why that makes sense. So these are basically, you can just go back and forth. Then let's make maybe one more together. I'll strongly recommend that you try exercise C at home, just to do it once yourself. So you're sure you have it in your fingers. And then we can go to G. And here it's much the same. You can say, okay, everywhere where there was fx before, you write x. And here you write 1 over x. Sorry, not x. You write everywhere where there was x, you write the inverse function plus 5, right? Okay, and again, we're trying to isolate this over here. So we're going to bring that to the other side, and we get x times f to the power of negative 1 x plus 5, do not forget our brackets, over 1 is equal to 1. Bringing x to the other side, dividing both sides by x, you get this. Minus x plus 5. So here we're almost there, and then you say 1 over x minus 5. So 1 to the power of x. And here you might already, well, consider this a little bit different, right? Because here x was not allowed to be negative 5, right? In our original function, which was y is equal to 1 over x plus 5, it tells us x cannot be equal to negative 5, because otherwise we're dividing by 0. And here in this case, x cannot be equal to 0. So while these are inverses of each other, there are some parts that, well, that move, that where the function, well, couldn't exist before, where there was an asymptote. Well, that one will also move and be in a different space. And basically you have a different domain for both functions. So here x is not allowed to be negative 5, and here x is not allowed to be 0. For the other exercises of 6, if you really want to make some more exercises, I strongly suggest that you also try to make exercise E and F. They're good practice, and they test if you truly understood how these inverses work. And especially when afterwards we talk about, well, functions after function and stuff, I hope you understand why these inverse functions are useful. Okay, that's it for this video. In the next video, we're going to deal more with function transformations and stuff. And in general, I know that the professor really likes you to be able to do these well. So follow along. And for the next one, you're also going to, well, we're going to graph some stuff in the browser. So make sure you have an internet connection. See you in the next video.